Okay, so last week we were working on elevator problems. This is kind of where we ended off. We were looking at some system problems as well, where you had stuff hanging over a pulley, which is going to be important for our lab, which I'm going to have a look at. I'm hoping we'll be ready to do it by Wednesday. If not, we'll probably end up doing it after Easter. Okay, but it also involves a pulley, so being able to do those system problems is going to be pretty important. What we're going to start looking at today is more along the lines of the vector nature of Newton's second law. Okay, so we're going to be looking at situations where the vectors are not collinear. Okay, so like an elevator, they're collinear. One is up, one is down. Okay, we're going to be looking at problems where they're not up and down, they're angled, and we have to sometimes do tail to head stuff. Okay, and things like that. So we're going to look a little bit more at that, move towards inclined plane problems, which is another type of, a very common type of Newton's second law problem that does involve you having to do a little bit of vectors, okay, but nothing like what we did, well, I shouldn't say nothing like, we might get the odd problem that was like a 2-vector problem like what you got for displacement in Unit 1, okay, so stuff like that. For right now, I want you to write this one down, okay, this is what we call a static condition problem. All right, so I want you to write it down, then we'll talk about what that means. Okay, so first off, what does the word static mean? Something is static. What is it? Not moving, not changing. Okay, like in English, if you were talking about like a static character, okay, they're a character who doesn't change throughout the play or movie or whatever it is. A dynamic one is one who does change. Okay, so we've dealt with dynamic problems already because this is the dynamics unit. Okay, oddly enough, we would have done some dynamic problems. Okay, but this, while still in the dynamics unit, is a static situation, which means the object word that is in question here is not moving. If that object is not moving, what is its acceleration? All right, everybody's holding up a 0. Good. So what's the net force acting on that object? Also 0. Okay, so if the net force acting on that object is 0, all the forces acting on that object add up to 0. Okay, so let's look at this particular static condition example. So we have a store sign that has a mass of 35 kilograms, and it's hanging from 2 different buildings. All right, so I'm just going to draw like, here's the, whoop, I don't know what's going on with that. Okay, so I'm going to draw this first building here. There's the first building, okay, and here's the second building. Right, and it says cable 1 is angled 55 degrees below the horizontal. Okay, so 55 degrees would probably look something like that. Okay, and it's attached to the sign. So here's the sign, okay, and it's 35 kilograms. So what I'm really doing here is drawing a free body diagram. Do you agree? Okay. And the second cable is horizontal and attached to a different wall. So it goes over here. Okay, so this is cable 1, and this is cable 2. They want the tension in cable 2. Okay. There obviously is tension in cable 2. It's pulling, okay? But it's pulling horizontally to the, which direction is this?
The right.
To the right. Okay. Now, the reason it has to pull horizontally to the right is because it's pulling against the other cable. Okay. Because this cable is horizontal, it cannot act to preserve or counteract any of the sign's weight. Because which way does weight act? Down. Okay, so if weight acts down, cable 2 is not offsetting this force that we haven't drawn on there yet, okay, the force of gravity. All right, so the force of gravity is 35 times 9.81, m times g, right, which we'll put there. 335 times 9.81. So we're looking at 343.35. Okay, newtons. So cable 2 can't do anything about that, which means which cable is holding all of that?
Cable 1.
Cable 1. But cable 1 isn't pulling up. Cable 1 is pulling 55 degrees below the horizontal. Okay? But since it does have, because it's angled, it has a vertical component and it has a horizontal component. Would you agree? Okay? It's pulling both to the left and up. Since it's the only part of this thing that's pulling up, its vertical component must be how many newtons?
$343.35.
Exactly. Why?
To counteract gravity.
Right, because the net force in this question is
0.
right. Okay, is there a lot of intuitive stuff that goes into this before we've even done anything except go m times g? Okay, once I do m times g, I've got to realize that it's only this cable that can exert a force equal to, but opposite that, so that my net force ends up being 0. All right, so 343.35 newtons is that side of this triangle. So what is this side pulling against? Think?
Cable 2.
Cable 2. If the object's not moving, the vertical forces have to offset and the horizontal forces have to offset. Okay? So whatever the force in cable 2 is, it's got to be pulling just as hard as cable 1 is pulling to the left. Okay? So is this just a trig calculation? Okay. So this is my opposite side. So if I go 10 to the minus 1 of 343.35 divided by, sorry, what am I doing here? That was wrong. Opposite over, sorry, I got to multiply. That finds the angle. I already know the angle. Sorry, guys. Whoop. Okay, so if I want the opposite side, sorry, I wanted to have the, come on, what's going on here? If I wanted to find the tan of 55, sorry, that was the way I was supposed to write. Tan of 55 is the opposite side, which is what I know, divided by the adjacent side, which is what I'm looking for. I'm just going to switch these two. So my adjacent side will be the opposite side divided by the tan of 55 degrees. Okay, so my opposite side was 343.35. Okay, so divide that by the tan of 55. Okay, so there's my other side. It's 2.4 times 10 to the 2 newtons. Okay, now that force is actually to the left, but they wanted the tension, and tension doesn't have to have a direction. It's just how tight the cable is. Am I done? I'm done. 2 calculations. Did that question seem like it needed more than that? Like when you first read that question, you're like, oh man, this is going to be a lot of math. 2 calculations. That's it. One of them was m times g. The other was a trig calculation. Okay? It's figuring it out. It's visualizing it out. You're going to get sick of hearing me say that. I'm going to keep saying it. Okay? It's about being able to see it, drawing the picture, figuring out what's going wrong, what forces are acting, what are they doing, are they offsetting each other, are they not? Okay? All of that stuff is crucial to solving static condition questions and any Newton's second law question. Okay, let's see what you remember from last week. Okay, so I've got this situation. 5 kilogram mass is hung over the pulley. It's attached to a 4 kilogram mass that is on a table where there is 32 newtons worth of friction acting against the 4 kilogram mass. Okay, I want the acceleration of the 5 kilogram mass. Okay, let's see what we remember from last week. Okay, so this is a system question. What do I need to remember about all system questions?
Both blocks are like connected, so it's the mass of the whole system.
Right. We always use the mass of the system when we're calculating the acceleration of any individual part. The reason for that is they have to go together. They're connected, so they have to have the same magnitude of acceleration. So I want to identify the forces that are acting here. That would be the force of gravity. Okay, so we have Fg here, m times g, so we have 5 times 9.81, which will be 49.05. I don't know what is going on with my smartboard. It's so weird. Okay, and then I'm going to have a force of friction here, okay, that is 32 newtons. Those are the only forces that matter? Yeah, I mean, there's a force of gravity and a normal force here on the 4 kilogram mass, but they offset each other, so I don't need to worry about them. All right, for right now, those are the two forces that are going to propel the system. So what I'm going to do is simplify my diagram down to this. 9 kilograms worth of mass being pulled this way by 49.05 newtons and this way by 32 newtons. Okay, so from there I can do the vector sum of all forces and get my F net. So that'll be 49.05 minus 32. Okay, so that should be 17.05, right? So 17.05 newtons, okay, for right now that way, but I'm not going to worry about that for now. Okay, now that I've done vector sum of all forces, now I want to do this because I got to realize that according to this red lettering that I forgot to erase, okay, F net is not only mass times acceleration, it is also the vector sum of all forces, and I already did that part, and I know that the vector sum of all forces is 17.05. So when I do that, I set that equal to m times a, that's that step right here, and then I divide it by the mass of the system, and I get 1.9 meters per second squared. But I put down on there. Why?
Because the blocks are falling down.
Well, the 5 kilogram block is falling down. The 4 kilogram block is sliding across the top to the right. But the question asked about the 5 kilogram block in particular. And if we go back up to the top here where the question was, to calculate the acceleration of the 5 kilogram block. In that case, I can put a vector on that because I know which way the 5 kilogram block is going to go. Had they asked for the 4 kilogram block, it still would have been 1.9 meters per second squared, but it would have been forward along the table or towards the pulley or to the right, or any one of those vectors would have been appropriate. Everybody all right with how that one worked? Okay. Again, fairly simple math. Right? We didn't do anything crazy there, okay? But we did have to remember, all right, I've got, you know, this mass, here's how they relate to each other, here's how the forces go together, right? And that's why we spend so much time on this concept. We gotta show you a lot of different ways that it applies so you gain that experience. Okay, we did, I think, one like this near the end of class on Thursday, where we had 2 blocks and they were connected by a rope. Okay, so I'd like to see what we remember from that one. So the total friction on the whole system is 120 newtons. The amount of friction on just the first block is 48 newtons. And I want you to calculate the acceleration of the 40 kilogram block, that can be like part A, and the tension in rope B. Okay, give you a few minutes to see how much you remember, because we did do one like that last week. Are the 2 boxes accelerating together? They have the same acceleration, yes? So does that mean I can simplify this diagram down to this situation? 100 kilograms being pulled this way by 150 newtons and resisted by 120 newtons. Okay. Can I find the vector sum of all forces on the system now? I can. 150 minus 120. 30 newtons forward. All right. Since I know that, and I know that F net is m times a, then I can go 30 divided by 100 and find that the acceleration is 0.3 meters per second squared forward. Okay, now I would have two significant digits there, so it would be 0.30, okay? But that's what I would have. Now that I know the acceleration of the system, I also know the acceleration of the 60 kilogram box and the 40 kilogram box, agreed? Now they want the tension in rope B. Here's what I have to understand in order to solve this question. Rope B is pulling on both boxes. It's pulling backwards on the 40 kilogram box. It's pulling forwards on the 60 kilogram box because it's connecting the two, right? So what I'm going to do is I'm going to look at just the 40 kilogram box because I actually have a little bit more information about the 40 kilogram box. So the 40 kilogram box is being pulled forwards by 150 newtons worth of force because the rope is directly attached to it. The question tells me that there's a force of friction on the first box of 48 newtons. And the other force acting on that box is the force in the cable, or the rope, or whatever it is. Everybody all right with that idea? That's the tricky part, is identifying that that rope is pulling on both boxes, pulling forward on the second box, pulling backward on the first box, because it's attached to the second box, and the second box is going to resist the first box. It's dragging along behind it. Agreed? So now that I know that, okay, and I also know that the acceleration of this box is 0.30 meters per second squared, what can I find about the 40 kilogram box right now? Right?
F net.
Yeah, I can find F net. I know the mass of the 40 kilogram box. I know the acceleration of the 40 kilogram box. So, as we said, in every Newton's second law question, you're going to use both of these methods. Right now, I have M and A, so I'm going to look at those, and I'm going to multiply them together. I'm going to say 40 kilograms times 0.3 meters per second squared. Okay, so 12 newtons forward is the net force acting on the first box, on the 40 kilogram box. That also means that the force applied, the 150, plus the force of friction, plus the force in rope B, add up to 12 newtons forwards. Since I know 2 out of the 3 of those forces, I just have to isolate the one I don't have, at force B. So I'm going to subtract these other 2 over to this side. I'm going to say that F net minus the applied force minus the force of friction equals the force in rope B. Now I do have to keep in mind, some of these are forward and some of them are backwards, and I have to reflect that mathematically with positives and negatives. Okay, so I'm going to have F net, which was 12 newtons forward, minus 150 newtons forward, minus negative 48 newtons, my force of friction, which was backwards. All right, I'm doing exactly what I said here. Okay, so if I do that, okay, so the force in that rope from the 40 kilogram box's perspective is 90 newtons backwards. Okay. Now it only asked for the tension, so I can actually leave it as 90 newtons. It didn't ask what's the force on box A. Okay. Everybody all right with that? Now, I could have also done that with the second box. I just would have had to subtract 48 from the 120 newtons of friction to find the force of friction on the second box. Otherwise, it would have worked exactly the same. Okay, again, how much math did we do there? Well, we did the same math we do in every single question. M times A, sum of all forces. We drew a free body diagram, right? All of those things. It just takes practice. Okay. Questions on what we did there? Okay. All right. So I want you guys to try this one. That's why. Okay, hang on. This is just going to flicker for a second. It's open in the wrong version of that program. Okay. So I've got 120 kilograms. Let's say this is, I don't know if you guys have seen, like at the McMahon Stadium there, they got like the big speaker thing that's suspended from cables over their center field. Okay. Sometimes at like hockey arenas, they have the big jumbotron suspended by cables from the corners of the stadium. So this is a big mass suspended by cables, okay, from these two posts. Right? There's a 100 degree angle between the two cables. And the mass they're holding up is 120 kilograms. I want the tension in cable A. Okay, it's suspended, so it's just holding it there. Okay, that 120 kilograms is suspended. Okay, what's the net force in this question? 0. It's a static condition question, just like the other sign hanging from cables question that we did. In this one, though, it works a little bit differently. This is still the same. Gravity is still doing this. Okay, Fg, okay, is m times g, and in this case, that's going to be 1177.2. Is that right? Yeah. Okay, 2 newtons. All right. So I've got those. Okay. I've got that force, but here's the thing. I've got two cables. So I'm going to say cable A I'm going to draw in red. Cable A is pulling up and cable A is pulling over. And since I'm splitting this up into, let's say, a red triangle and a green triangle, that are, whoops, supposed to be equal. That was really bad. Only because I'm a terrible drawer. Okay, so they each have a triangle that looks like this. Everybody all right with that? This angle then, for each one of them, is 50 degrees. Okay, even for the red triangle, because I'm splitting that 100 degrees in two. What else do I need to split in two? Here's the most common mistake on this question. People get this bar, they identify that there's two cables pulling on it, and then they say, okay, for the red triangle, this side is 1177.2 newtons. But if that's the case, this is 1177.2 newtons. And then I have a net force of 1177.2 newtons. Didn't we just say the net force was 0? If I write it like this, that mass is flying upwards at 9.81 meters per second squared up. It ain't doing that. Okay? And it's not doing that because those forces are not 1177.2. They are half of that. Okay, everyone kind of with me there? Okay. If each one of these is pulling over and up, and the object's not moving, each one of their vertical components holds half the weight of that object. All right, so I've got to take my 1177.2 and divide it by 2, and now I know that each side, and I'm dealing with this side here, is 588.6 newtons. Right? Now I can calculate the tension in cable A, which would be identical to the tension in cable B. It's just a matter of doing some trigonometry. In this case, I'm going to go cos of 50 degrees equals the adjacent side, 588.6, over the tension in cable A. And then I'm just going to flip these. So the tension in cable A equals 588.6 divided by the cos of 50 degrees. All right, so each cable is going to have 9.2 times 10 to the 2 newtons worth of tension in it. Okay, did I lose anybody there? Okay, where did I lose you?
I just, like, I know what I did wrong, but then, like, I get it now, but I know before I was wrong.
Okay, but was it the double?
Yeah, I was splitting it in two, like, I divided, like, the two angles in half, but then I forgot to divide the
The
weight in half.
force of gravity by 2,
Force of
yeah.
gravity in half.
Okay, and it's pretty common. It's actually common because it's an inexperienced mistake. We haven't done that many of these, right? And it takes a while before you look into a question and go, oh, right, they're splitting that. Okay, that just takes experience. It takes doing a lot of these to see those little tricks that can come up in a question like that. All right? Okay, we're not going to quite get to inclined planes today, but I would like for you guys to work on a few questions from the digital workbook, and I'm going to show you which ones I want you to do, because we're going to look at some vector-related ones today, and then we'll get to inclined planes probably tomorrow. And you will have a quiz tomorrow. Okay, so let's say that I would like you to do 1 through 4 for right now on that sheet. Okay, they all have a vector part to them. Either it's, you know, finding vector components or doing a little vector addition. Okay, and they're also Newton's second law questions. Okay. Okay, so on this one here, okay, we've got the truck. Okay, like so. And it's being pulled at a 45-degree angle. Okay, and we know that there are 2,000 newtons worth of force in that cable. Okay, they tell me friction is opposing with 500 newtons. Friction has to act straight backwards because, well, we have to assume that it's a level road. Okay, that they're not going up a hill or anything. All right, what do I have to realize about this question? Is that 2,000 newtons worth of force acting directly against the 500? It's not. Here's the other thing. The car, or truck, or whatever it is not moving vertically. So what that means is that this vertical component of the 2,000 newtons is equal to the force of gravity. Okay? But it's negative. Which means it doesn't matter. This car's not moving vertically. Okay? Those two things are going to cancel each other out. But this 2,000 newtons worth of force also has a horizontal component. That is acting directly against friction. Can I calculate how much that is? Yeah, I can. So I'm simply going to go cos of 45 times 2,000, and I'm going to know what this side is. Okay, so there's 1,414.21 newtons worth of forward force from the tow truck. 500 newtons worth of force backwards from friction. Okay, can I now calculate the net force acting on this truck? I can. Vector sum of all forces I've already done. The vertical component of this I've already established cancels off with gravity. Truck or car isn't moving vertically. Now, the only two forces to vector sum are the 1414.21, which I'll make positive because it's forwards, plus negative 500 newtons because it's backwards. So that's going to be 914.21 newtons, I believe, if my mental math is right. Okay, forwards. All right, now I know the net force because I did vector sum of all forces. Okay, and I did a bunch of other vector sum stuff over here. Okay, when I did my trigonometry, well, now I can say acceleration equals 914.21, okay, divided by the mass of the car, which, sorry, I didn't write in my free body diagram like I did, 1,500 kilograms. All right, that gets us our positive 0.609. What the heck is going on? Meters per second squared. And that would be, positive would be forwards in that case. Does that sort of make sense? Just a bit of vector stuff. That is exactly the kind of thing that's going on in questions 1 through 4. Okay? It's not super complex, I gotta go draw tail to head kind of vector stuff. It's more, can I see into this situation kind of vector stuff, right? And that is especially true on question number 4. Okay. Anybody done all 4? Okay, give you a few more minutes then. Any other ones we need to go through? Okay. What are the key words in number 4?
Constant speed.
Constant speed. Okay, does it matter what that constant speed is? Makes no difference. What's the net force in this question? 0. Okay, because if you're moving at a constant speed, your acceleration is 0. So what that means is, okay, here's our fish. He's not happy, okay, because he's got a hook in his face, okay, and he's being pulled at an angle, all right? But it says here that he is moving horizontally, right? So he's moving horizontally, which means there must be a force backwards as well. Which force is that? Okay, so they tell me that there's friction opposing the motion, which we know is directly forwards, of 80 newtons. So is this force the force of friction? All right, so if that's the force backwards, okay, and what did they tell me this angle was? 45 degrees, and I'm looking for this force of tension right here. How big is this force? 80 newtons. It's moving at a constant speed. Therefore, the force forward and the force backward have to be equal but opposite in direction. So that tells me that this side then is 80 newtons. And once I know that, I can use it to get the tension in the line. Okay? It's another one that doesn't involve a lot of work, okay, but it involves a fair amount of insight. Being able to make that connection that because the net force is 0 and the fish is moving horizontally forwards, that the force forward and the force backward, and you're given the force backward, must be equal. Once I know that, then I can calculate that force of tension, okay, because I know the angle, so I'm going to have the adjacent side, force horizontal, okay, divided by the cos of 45, or the sine of 45, because it's 45 degrees. Okay, so if I take that 80 newtons, okay, and divide that by the cos of 45, okay, I get 113 newtons, 45 degrees from the horizontal. or just 113 newtons because it did ask for the tension. Okay. Why can I have 3 significant figures in that? It's another thing that people do wrong on this question.
Because you don't use the velocity.
Right. You don't use the 0.85. It's never part of a calculation. Okay. Therefore, it doesn't affect the accuracy of your final answer. Okay. Second trick in that question. All right. Does everyone understand that question now? Okay. Because it's tricky, right? Like there's not a lot to it, but it's still tricky. And we have to be able to diagram it in order to kind of get what's going on in that particular question, right? This is the vector nature of force. We have to see the effect of the different forces. Which direction is this force acting? How does that affect the object it's pushing or pulling? Okay? That's probably the most complex part of all of these questions. Okay, now, this one here is probably one of the easier ones, okay, that you would have, right? But you haven't been asked to calculate a mass yet, so in that way it's a little bit different, right? But there's no complex vector analysis. There's forward and backward, right? Give that one a try. See if we can do it before the bell goes today. Okay, so this one's pretty straightforward. Okay, just draw your forces out on your free body diagram. Okay, so we don't know what the mass is, but we do know that there's a 300 Newton force, a 250 Newton force, and a 175 Newton force. Right, get your F net by simply adding those together. So 300 plus 250 minus 175, and then you take that and divide by the acceleration you were given. Guys, can you please take that back? The teacher's supposed to bring that to me.
Oh.
Yeah, so please take it back and tell the teacher that's got to come back with them. Okay, does that make sense? Okay. So, just so you know, right, we take that, we divide it by the acceleration, we'll have the mass, which ends up being 239 kilograms. All right, so check out the quiz tonight. Okay, we'll be doing a lab on Wednesday, but we're moving on to inclined planes tomorrow, okay, for what we're going to be covering that's new.